Hello everyone, welcome to my presentation to our work Beyond the Front Page, Measuring Third-Party Dynamics in the Field. My name is Tobias. I'm a third-year PhD student in a joint PhD program at the Institute for Internet Security and Ruhr University Bochum. This is joint work with Martin Degeling, Thorsten Holz and Norbert Pohlmann. Okay, let's just jump right into the presentation. What do researchers usually do if they want to measure some privacy phenomenon like user tracking or the effects of privacy regulation like the CCPA or GDPR on the web? Usually researchers utilize a given top list that creates a ranking of the most popular domains using a given matrix. Then they crawl the top n domains on these lists and analyze if a given phenomenon is active on any of these sites. In other words, they linearly iterate over the most popular domains and check whether these utilize a given technique. However, we all know that the web is not a simple linear collection of websites based on a ranking, and we also know that each website itself can have a complex structure. For example, let's take a look at a common structure of a website of a scientific conference. We have the homepage or the landing page, which provides basic information on the conference and its content, and we have several subsites which provide much more in-depth data. For example, if we want to learn more about the program, we go into the program site, which has information on the speakers, the schedule, which themselves are sites on their own. This example shows that a website is not only the landing page of this site, but that each website can have a quite complex structure of subsites. Keeping in mind this scenario, we asked ourselves, do a citation made for a landing page of a domain hold for the web pages or for further web pages on that domain? For example, if we observe or don't observe a given phenomenon on the landing page of a domain, does that automatically mean that we will or won't observe the same phenomenon on further web pages of the same domain? To answer this research question, we performed a measurement study. To account for the more complex structure of websites presented in the previous example, we used a slightly different measurement setup in contrast to previous work. Similar to previous work, we scaled our measurement horizontally, which means that we used a top list, in our case the Trunco top list, and used the top 10,000 domains of that list as our seed domains. In contrast to previous work, we not only visited the landing page of each of these domains, but performed a more in-depth crawl of each website. In the first step of our measurement, we visited the landing page of each domain in our top list. By landing page, we mean the website that is usually visited first on a website, for example, google.com. However, we then collected 75 first-party links on each website, which we then used for our later analysis. We call these first-party links subsites to display the hierarchy between the landing pages, which are the pages on the top list, and the pages we then visited. We collected these links to account for the complex structures of a website, as previously described. At the same time, we populated a browser profile by visiting random websites from the Trunco list. By browser profile, we mean that we filled the cookie jar, that the browser profile has a browsing history and other properties that the vanilla browser does not show. If you want to know why we collected 75 first-party links and why we populated the browser profile, I would like to refer you to our paper in which we perform a pre-study to determine these properties. Finally, we used OpenVPN to load the browser profile and to visit each collected link. We visit the links from 3 different regions, from the United States, from Germany, and from Japan. Each measurement crawl, we also visited the landing page aside from the subsites. Before we dive into our results, let's take a quick look at the collected dataset. Overall, we visited 1.5 million distinct URLs from the 10,000 domains of the Trunco list. The crawls generated over 4.5 terabytes of data. As you can see, the crawls in the different regions are quite comparable. We observed a similar amount of third parties, cookies used by these third parties, and overall visited websites and subsites. Slightly deviations of visited websites and subsites can be attributed to crawler crashes or that specific websites were not present at the time of the crawl. Furthermore, it seems that cookie setting behavior is not really impacted by the region. Side note, I want to point out that in our paper we performed a short classification of the observed cookies, and we found that 99% of the third-party cookies are used to track users or to provide them targeted ads. After introducing our measurement approach and the measure dataset, let's take a look at the results. Let's start with the comparison of third-party cookie usage on landing pages in contrast to subsites. Remember that by landing page we mean the sites that are on the Tranco top list, and by subsites we mean first-party links from the landing page. The light gray bars demonstrate the third-party cookie usage on the subsites, and the darker gray bars demonstrate the same usage on the landing pages. As you can see, landing pages use far less third-party cookies than the respective subsites do. Also, we can see that some website categories like news websites use more third-party cookies than others. This is in line with previous work. Our results show that subsites show a different behavior when it comes to specific phenomenons, in our case, third-party cookie usage. To increase the readability of our slides, from now on we will only take a look at news websites. However, in our paper we provide an overview of many more categories, and there's no substantial difference between the categories other than news websites tend to use more of the privacy invasive techniques. By no difference I mean that in all categories the subsites tend to use more of the privacy invasive techniques in contrast to their landing pages. Based on these results, we wanted to know if other privacy invasive technologies are also more present on subsites than on landing pages. To do so, we replicated previous work using our data. I want to highlight that we don't claim that these replications are sound or complete, but that we tried our best to replicate the main findings of the work. As we've just shown and compared to previous work of Dabrowski et al., subsites make more use of third-party cookies than respective landing pages. I want to point out that for all measurements we either analyzed only the landing pages to create the comparison or used the same amount of subsites. Based on our measurement, we found an increase in the usage of user tracking technologies on subsites in contrast to landing pages by more than 6%. If we would only consider the landing pages in our experiment, we would get comparable results to the named previous work. Previous work used lists that combine known tracker URLs, which are often used by tools to block these trackers. Measurements of these trackers on the landing pages are comparable to the named previous work. However, on subsites we found an increase of the stated 6%. However, the subsites show an increased usage of these URLs of 6%. Device fingerprinting is a technique used to track users based on unique properties of their devices. Currently, many different properties of a device are used to compute the fingerprint. Examples are the installed fonts, the used browser extensions, the desktop resolution, and others. We measured the presence of such scripts on landing pages in contrast to the subsites. In contrast to previous work of Engelhardt and al., which were the first ones to identify device fingerprinting on a larger scale, we found that in contrast to landing pages, subsites use way more of such scripts. I have to mention that the results of Engelhardt and al. Are from 2016, and we only found very few of the scripts they identified in our dataset. To make the comparison, we used a common script that is nowadays used to compute these fingerprints. Finally, we analyzed cookie syncing, which is a technique used by adtech companies to share user identifiers. For this analysis, we compared our results to a different study we performed on cookie syncing. We measured an increased usage of cookie syncing attempts on subsites by 15%. Overall, we found an increased usage of privacy-invasive technologies on subsites in contrast to landing pages. We were curious whether subsites show different behavior when it comes to the usage of privacy-invasive technologies in contrast to their landing pages. To answer this research question, we performed a measurement study that accounted for the complex structures of a website. We've just shown measuring only the landing page of a given website, it might hide the actual scale of a given privacy-invasive phenomenon. Our results show that landing pages make less use of privacy-invasive technologies in contrast to their subsites. This is probably because the subsites of websites often include other features than the landing pages do. For example, news articles often include a comment section or ways to share the article using social media, and therefore there might be some other tracking techniques in these sites. Our work has implications for future work that wants to measure security and privacy aspects of a website. We should always consider to use a more vertical measurement setups, in example to scroll subsites, in contrast to a horizontal setup where only landing pages are measured. As previously mentioned, it seems that third parties that are embedded on subsites behave differently as if they were embedded on landing pages. This raises the question if service providers are in control which third parties are embedded into their websites. Furthermore, and maybe more importantly, if we take a look at the design of previous measurement studies, we see that most visit a website once, check if a phenomenon is present or not, and draw conclusions from that. However, we all know that the web is really dynamic, and therefore, if someone tests for the presence of a given phenomenon, this hides a lot of complexity. Let's take online advertisement as an example. The ad that the user sees when visiting the website is determined in real-time bidding. The winner of this bidding process can deliver the ad, and based on different outcomes of the ad auction, different third parties might be embedded. Now, not all of the embedded third parties will use the same partners and the same technologies, and therefore, if we visit a website once and take a look at the outcome of the visit, it might hide the complexity if other third parties would win the ad auction. This example highlights that when the service provider delivers the website to the client, the service provider does not know upfront which third parties will be embedded into the website. The research question that we addressed in the paper tries to tackle this challenge, and we asked ourselves, to what extent can service providers control which third parties will be embedded into their services? These questions can be crucial for service providers who want to account and who need to audit which third parties are embedded into their services. For example, for compliance reasons with given legislation like the GDPR. In our dataset, only 7% of the analyzed domain always used third parties that are located in the United States, Canada, or within Europe. Measurements have shown that the same resources are sometimes loaded from different servers, for instance, once from a server within Europe and once from a server in Singapore. In this case, data of European users might leave the European Union, and therefore it might pose a problem for the service provider. Let's start with an example so we all know what we're talking about. We took this example randomly from our dataset, and we don't want to blame any of the parties, and especially not Adidas. It's just a good example of what we found in our analysis. Let's assume we visit adidas.com. As you can see, adidas.com relies on several third parties to deliver their product. In the modern web, it's quite normal to rely on third-party code, and there's no problem with the given third parties whatsoever. Furthermore, it's very likely that adidas.com is aware of these third parties, as the website directly embedded these services. What happens now is that MediaMarkt loads additional partners it relies on. These partners are the fourth party of adidas.com. It is not clear if Adidas is aware of these partners, and it's also not clear if these exact partners are always loaded by MediaMarkt, or for example, if they are only loaded based on whoever wins an ad. On the contrary, in our example, Adobe shows a very different behavior. Adobe loads only one additional partner, but that partner again loads another partner, and so on and so forth. You can see in the end of the chain, Adobe is loaded again. This does not mean that there's a loop, it just shows that Instana also utilizes a service of Adobe. As you can see, the high dynamic of the web enables different behavior of third parties. Some might rely on several third parties, others might only rely on one other third party, which again loads other third parties, or it can be a mix of both. Or there can be trees that have branches that are really deep, or in other words, that are quite long. To analyze the loading dependencies of the third parties and to build the trees, we analyze three methods that can be used to dynamically load code. It is worth to highlight that there are several ways to dynamically embed third-party objects into websites, but most of these objects cannot themselves load additional code. For example, JavaScript can easily load additional script code, but an image cannot load additional code. Analyze the JavaScript call stacks in the browser to understand if a given JavaScript loads other scripts it depends on. For example, if a JavaScript loads another library like jQuery, which it needs. Furthermore, we analyze iframe hierarchies, which are created if one iframe embeds another iframe. We analyze such hierarchies by utilizing OpenVPN's feature to store them, and then by analyzing the source tag of each iframe. We look at the dependencies of cascading style sheets and look which script imports another script. Eventually, we will know all the loading dependencies of embedded third-party objects on a website. We use these dependencies to build trees that are similar to the one in the example that I've shown you. Hence, these graphs resemble all third parties embedded into a website, and they also show who loaded each party. In the following, we provide an in-depth analysis of these trees. Let's start with the depths of each branch in the trees. Most of the observed branches are of depth 0, which means that the embedded third party did not include any partners. However, over 40% of the observed branches have depths of more than 1. As you can see, most branches in our dataset are rather short, but we found some of depths of up to 8. While these third parties are not a problem themselves, we asked ourselves if each third party will load the same partners every time the user visits a website, or if settings on the client or other environmental effects like the date or the region of the visit will influence this. To analyze that, we looked at the deterministic of our trees. By deterministic, we mean if a service provider can a priori say which third parties will be loaded if a given third party is inserted into a website. To do so, we analyzed the children of each directly embedded third party. We analyzed this from a local point of view in which we only looked at the third parties embedded on one single website and looked at the embedded third parties. Furthermore, we took a more global point of view in which we looked at a single third party and at all branches of this third party on all visited websites. Hence, we can understand if a given third party always behaves the same no matter on which website they are embedded, or if there are differences. For example, different ads that are embedded based on the content of the website. We found that almost 2/3 of the observed third parties included children only in some of the branches. On a global scale, we see a slightly different view, but it still does not provide a sufficient overview of the behavior of a third party. I want to highlight the steep increase of 6 or more new children in each branches, meaning that we have a very long tail distribution and that some third parties are not deterministic at all. The implication for future work of this is that visiting a single website once will only provide a limited view of those third parties that might be embedded. From the service provider's perspective, this is troubling because they cannot really know which third parties might be included into their services. Finally, the region of of the measurement does not impact the fluctuation of a third party. This means that legislation like the GDPR does not seem to impact a third party in terms of partners they rely on. While most loaded third parties are not very deterministic, we wanted to understand the depth of a branch that's created by each embedded third party. The figure shows the depth of the branches created by each company. The figure is scaled for each company, so we can understand the depth that's created by the company, but the figure does not show the overall inclusion of these third parties. You can see most third parties create branches of depth 0. This is expected because most websites directly use a service provided by a company. For example, they use Google Fonts. However, edtech companies offer a more widespread tree depth. This is because they usually load other third parties, for example, the companies winning the ad auctions or some technology that is used to counter ad fraud. These results show that service providers who carefully select the third parties they depend on might have some control of other third parties that might be loaded. However, at the end of the day, most websites rely on the revenue they create by ads, so they have to choose ad networks, which result in deeper trees. The second question that we wanted to answer with our work was to what extent service provider can control the third parties that are embedded into their service. We analyzed this by building third-party trees. Third-party trees resemble the loading dependencies of each third party that is embedded into a website. With our research, we have shown that the definite set of third parties that is loaded by the client is determined at loading time. This is nothing new, but our work shows that these loadings are often not deterministic and service providers probably don't know which third parties will be embedded into their services. From a service provider's point of view, this might be troubling because they might have to account for each third party that is loaded onto their website under the given law. Furthermore, the loaded third parties might harm the users by, for example, extensive tracking or malicious content. Hence, the service provider might endanger their users by their reliance on these third parties. Okay, finally let's discuss the overall takeaways and findings of our work. In the first part of our paper, we have analyzed the different usage of privacy-invasive technologies on subsites and landing pages. Our results show that subsites make substantially more usage of such technologies in contrast to the landing pages. The important takeaway of our paper is that future work that wants to assess privacy phenomenon on the web should also consider to visit subsites and not only landing pages, because that might hide the real scale on the usage of the phenomenon. In part of our work, we analyzed the loading dependencies of third parties. We have shown that embedding a single third party into your website might lead to the successive loading of many more third parties. We have also shown that these loading dependencies are not always deterministic. This non-deterministic means that the service provider does not know which third parties will be embedded once the user loaded the full page. One implication of this dependency is that service providers often lose control over their services, at least to some extent. Basically, this means that the service providers have to trust the third parties and that auditing them is not always straightforward. This is troubling for all service providers who want to account for the third parties that are loaded on their service, for example, if they want to protect their users from online tracking. And this concludes my talk. Thanks for your attention. I hope you had as much fun as I had. Now I am ready to take your questions.